Welcome. This is a lecture on the formation and structure of our solar system. The solar system is about 4.5 billion years old. We use radioactive decay to measure how old rocks are, and we found that planets, asteroids, and comets are all about the same age. We find a similar age for the Sun. However, we don't use radioactive decay for the Sun. We use other methods. A simple way is to look at how much hydrogen and helium is present in the Sun, and knowing how fast they react, we can calculate the age of the Sun. Any hypothesis devised to explain the origin of the solar system has to account for the following facts. First, the solar system is flat, with all the planets orbiting the same direction. Second, there are two types of planets. We have rocky ones closer to the Sun and gaseous and icy ones farther away. And third, the composition of the outer Jovian planets is similar to that of the Sun. Number 4, the composition of the inner planets is similar to the Sun in that they both have iron, nickel, magnesium, silicon, and sulfur. The inner planets, however, do not have hydrogen and helium. Number 5, all the bodies in the solar system are less than 4.5 billion years old. The current accepted hypothesis that takes all of these into consideration is the solar nebula hypothesis. A nebula is a bunch of gas in outer space that is somewhat clumped together. The current hypothesis states that the solar system came from an interstellar cloud of gas and dust that was rotating and flattened into a disk. The inner part of the disk became the Sun, and the outer parts became the planets. Take a look at the word interstellar cloud. Inter means between, stel means star, so this is a cloud of gas found between stars. The cloud was estimated to be about a few light years in diameter. Remember, a light year is the distance light can travel in 1 year. It also had about twice the present mass of the Sun. The composition of the cloud was similar to that of the Sun, about 71% hydrogen and 27% helium. And there were traces of other elements in the gas as well. The cloud also contained tiny particles called interstellar grains. These are materials that are ejected by stars. They can range from about a micrometer to about the size of a grain of sand. Scientists believe that the interstellar grains are mixtures of silicates. Silicates are minerals that have silicon and oxygen in it, much like quartz, which can be found on the beaches on Earth. In addition to silicates, iron compounds, carbon compounds, and water ice can also be found in interstellar grains. Gravitational attraction between these particles in the densest part of the clouds caused it to collapse inward. Since the collapsing cloud was rotating, it became a disk. The collapse took a few million years. The disk that developed was the solar nebula and had a bulge in the center, which became the Sun. The outer parts of the disk became the planets, their satellites, which are their moons, asteroids, and comets. The inner part of the solar nebula around the emerging Sun were very hot, and the outer parts were very cold. In the colder areas, the gas cooled quickly enough that it condensed to form liquid or even solids. In the disk, the temperature dropped low enough everywhere to condense tiny crystals of iron and eventually rocky materials. Only the outer planets for the disk, Jupiter, Saturn, Uranus, and Neptune, did the temperature drop low enough to condense the ices, which are methane, ammonia, and water ice. In a process called accretion, the tiny particles formed by condensation began to stick together to form large aggregates. As accretion continued, large particles called planetesimals formed, which ranged in size from millimeters to kilometers. As planetesimals moved around within the disk, they eventually collided. If the collisions were gentle enough, the colliding planetesimals stuck together and grew in size. The orbits of the growing planets became nearly circular around the Sun. In the inner part of the nebula, the planetesimals were primarily of rock and metal. So as you can see here in the first picture, there's a lot of dust and grains in the nebula. You can see it's rotating and the Sun is starting to form. As time goes on, these dust grains will slowly clump together to get planetesimals. As time goes on, the planetesimals grow in size and they will start collecting more planetesimals, making the planets larger. Since rock and metal are not as abundant as the ices, the planets that form from them are rather small, so the 4 inner planets are pretty small. In the outer part of the disk, the material was much more abundant since it was cold enough for the formation of ices. This caused the planets to be much larger. Once the outer planets grew as large as the Earth, their gravities increased and they were able to maintain hydrogen, and helium in their atmospheres. As planetesimals struck a growing planet, the impacts converted the gravitational energy into heat energy. The planets grew hot, for the rocky and metal materials became molten. The more dense materials sank to the planet's center to form its core. The lighter rocky material formed the mantle and the crust of the planet. This process is called differentiation. This also explains how the Earth's core is mostly iron, and the crust is mostly lighter density materials such as silicates. Moons of the outer planets are probably formed from planetesimals orbiting the planets. Most of the moons of the outer planets are composed of rock and ice. They have solid surfaces and are generally cratered. Some of them will show signs of volcanic activity. The final stages of the planet formation was a barrage of planetesimals that blasted out large craters in bodies such as the Moon. The planet building used most of the planetesimals, but a few survived. They became the moons, asteroids, and comets. The last stage of the planet formation was the formation of the atmospheres. The outer planets probably captured most of their atmospheres from the solar nebula. The inner planets have masses way too small to capture gas from the nebula. Therefore, they were deficient in hydrogen and helium. Venus, Earth, and Mars probably created their initial atmospheres through volcanic eruptions. With every volcanic eruption, gases are emitted. Some of their atmospheric gases may have come from falling comets and icy planetesimals that vaporized when it came in contact with the planets. A few 100,000 to 1,000,000 years were needed to form the planets from the solar nebula. This is a really short time considering the history of the solar system, 0.02%. The intense heat of the early sun probably created a great flow of gases outward from its atmosphere. This solar gas encountered the residual gas and dust of the solar nebula and swept it outward to the outer fringes of the solar system. The sun is a star. Any star is a ball of incandescent gas whose heat and light originates from the nuclear reaction of its core, fusion. The sun contains more than 1,000 times the combined masses of all other bodies in the solar system. In other words, it is huge compared to all of the other objects in our solar system. Since the sun has most of the mass in the solar system, its gravitational force holds all of the other bodies in the orbital patterns around it. The sun is about 71% hydrogen and 27% helium, and it contains very small proportions of nearly all other chemical elements in vaporized form. In order for a body to be considered a planet, the following three must be true. It needs to orbit the sun, it has to have sufficient mass for its self-gravity to overcome rigid body forces, therefore it makes it nearly round, and 3, it has to clear its neighborhood of its orbit. Pluto, unfortunately, does not meet these requirements. Unfortunately for Pluto, it does not meet number 3. It did not clear its neighborhood around its orbit. All planets follow a nearly circular orbits. Technically, they're ellipses, but they are very close to circular. The planets orbit in a counterclockwise direction when viewed from the Earth's north pole. Each planet also spins on its rotational axis, generally in counterclockwise direction. Venus is an exception to this rule. Venus rotates in a clockwise rotation. This is called retrograde rotation. Uranus and Pluto, unlike other planets, have very large axial tilts relative to their plane of the solar system. There are 2 classes of planets in the solar system. The first class of planets are called the inner planets: Mercury, Venus, Earth, and Mars. These are small rocky bodies with relatively thin or no atmospheres. Since they have a rocky surface, they are called terrestrial planets. The second class are the outer planets: Jupiter, Saturn, Uranus, and Neptune. These are gaseous, liquid, or icy. These planets are called Jovian planets. The outer planets are much larger than the inner planets, and they have a deep, hydrogen-rich atmospheres. Remember, Pluto is not a planet, nor does it fit this description. It is not large, and it does not have a deep, hydrogen-rich atmosphere. This shows you a scale model of the different sizes of the planets. Notice the sun's surface is right here. Also notice that the outer planets have rings, which are not always depicted in pictures. In astronomy, rock is material made up of silicon and oxygen, known as the silicates, in addition to other heavy elements such as aluminum, magnesium, sulfur, and iron. Ices are frozen liquids and gases such as water ice, frozen carbon dioxide, frozen ammonia, and frozen methane. The inner planets were mostly rock because it was too warm in the inner part of the solar system for gases such as ammonia, carbon dioxide, and methane to condense and mix with rocky material. The outer planets have no true surfaces. Their atmospheres thicken and become denser with depth and eventually liquefy. There is probably no sharp demarcation between gas and liquid. In the deep interior of the gas planets, the liquid is possibly compressed enough to form a solid core. There is probably no sharp boundary between liquid and solid. Jupiter, Saturn, Uranus, and Neptune were also called Jovian planets due to their similarities in Jupiter. Pluto is not a Jovian planet. Pluto was also not named after Mickey Mouse's dog. However, the dog was named after the dwarf planet of Pluto. Pluto was a Roman god of the underworld. Most of the planets, except for Mercury and Venus, are orbited by satellites. A satellite is an object that orbits another, so it could be a moon. These moons move along approximately circular orbits that are in the planet's equatorial plane. A few exceptions. Uranus's moon and Pluto's moon have orbits that are tilted like the planets themselves. From 2005 to the present, a few bodies have been discovered beyond the orbit of Neptune. These dwarf planets, called Plutoids, are similar to Pluto in size and composition. Both asteroids and comets are smaller than planets. The asteroids are metallic or rocky bodies with diameters of a few meters to about 1,000 kilometers. Most asteroids are located in the gap between the orbits of Mars and Jupiter. This region is known as the asteroid belt. This is most likely a failed planet. Comets are icy bodies about 10 kilometers or less in diameter. As the comet nears the sun, the heat vaporizes much of the ice in comets and develops huge tails of dust and gas. Most comets orbit the sun far beyond Pluto in a region of the solar system known as the Oort cloud. The Oort cloud is a spherical region that surrounds the solar system and extends from about 40,000 to 100,000 AUs. An AU stands for an astronomical unit. 1 AU is the average distance between the Earth and the Sun. There is also a disk-like swarm of icy objects lying beyond Neptune's orbit. This region is called the Kuiper belt. As you can see here, the Kuiper belt is just beyond Neptune's orbit, and the Oort cloud is beyond the Kuiper belt. Scientists can use spectra or wavelengths to determine the composition of a planet's atmosphere. Remember, every element gives off a different wavelength. On Earth and the Moon, we can also use seismology and the magnetic fields to determine the composition of the interiors. To make educated guesses about the interior of the planets, scientists can use the densities of the planets. The density of a planet is its mass divided by its volume. Both mass and volume can be determined relatively easy for a planet. A planet's mass can be determined from its gravitational attraction on a second body, such as a moon or spacecraft orbiting it. This is done by applying Newton's modification of Kepler's third law. A planet's volume is determined by using the relationship of volume equals 4 times pi times the radius cubed divided by 3. Once we know the planet's density, we can use densities of known substances to figure out the interior composition. The interterrestrial planets have densities very similar to that of the Earth, ranging from 3.9 to 5.5 grams per centimeter cubed. The outer Jovian planets have much lower densities, ranging from 0.71 to 1.67 grams per centimeter cubed. So we can conclude that the inner planets contain large amounts of rock and iron, while the outer planets have mainly low-mass materials in the gaseous and liquid forms. The spectral analysis of the Jovian planets shows that the Jovian planets have hydrogen, helium, methane, ammonia, and water. The outer planets probably have solid cores of rock and some iron. The data also furnishes clues as to the origin of the solar system. It seems that the Sun and the planets formed out of the exact same material. Jupiter and Saturn have compositions that are almost identical to the Sun. The inner planets would have compositions similar to the Sun, here's the key phrase, if we were to remove the Sun's hydrogen and helium. The gravitational attraction of the inner planets is not strong enough to hold on to these very low mass gases because the inner planets themselves have very low masses.